Hello and welcome to Math Zone African Motives. In this tutorial, we will be working through a Mathematics N5 past paper. Our goal is to provide a clear step-by-step walkthrough of each question, ensuring we explain the formulas and concepts involved. We will address every part of the questions, use color-coded highlights for clarity, and if we find any discrepancies in the provided solutions, we will explain and correct them. Let's get started with question 1. In question 1, we are asked to determine the value of a limit. The first part, 1.1, asks us to find the limit of x over the natural log of 2x minus 1, all cubed, as x approaches infinity. The first step in solving any limit problem is to attempt to substitute the value x is approaching. In this case, that's infinity. Substituting infinity for x, we see that both the numerator and the denominator approach infinity. This is an indeterminate form of type infinity over infinity. When we encounter an indeterminate form like this, we can use a powerful tool called L'Hopital's rule. L'Hopital's rule states that the limit of a quotient of two functions is equal to the limit of the quotient of their derivatives. Essentially, we can take the derivative of the top and the bottom separately. So let's apply this rule to our problem. First, we need to find the derivative of the numerator and the denominator. The derivative of x with respect to x is 1. The derivative of the denominator using the chain rule is 3 times the natural log of 2x minus 1 squared, times the derivative of the inner function, which is the natural log of 2x minus 1. The derivative of ln u is 1 iu times du dx, which gives us 1 over 2x1 times 2. Combining these gives us 6 ln squared of 2x minus 1, all over 2x minus 1. Now we substitute these derivatives back into our limit. The limit becomes the limit of 1 over our new denominator. We can rewrite this by multiplying by the reciprocal. This gives us the limit of 2x minus 1 over 6 ln squared of 2x minus 1. Notice that this is still of the form infinity over infinity. Since we still have an indeterminate form, we must apply L'Hopital's rule again. We'll find the derivatives once more. The derivative of the new numerator 2x minus 1 is 2. For the denominator, we use the chain rule again. It's 6 times the derivative of ln squared of 2x minus 1, which we just found. This gives us 6 times 2 ln of 2x minus 1 times 1 over 2x minus 1 times 2. Simplifying, we get 24 ln of 2x minus 1 all over 2x minus 1. Plugging these new derivatives back into the limit gives us the limit of 2 over our new denominator. Again, we rewrite this by multiplying by the reciprocal, resulting in the limit of 2x minus 1 over 12 ln of 2x minus 1. And again, we have the indeterminate form infinity over infinity. So we must apply L'Hopital's rule a third time. The derivative of 2x minus 1 is still 2. The derivative of the denominator, 12 ln of 2x minus 1, is 12 times 1 over 2x minus 1 times 2, which simplifies to 4 over 2x minus 1. Substituting these into our limit for the last time, we get the limit of 2 over our new denominator. Multiplying by the reciprocal gives us the limit of 2x minus 1 over 12. Now we can substitute infinity. This gives us infinity minus 1, which is infinity over 12. Infinity divided by 12 is still infinity. So the final answer is that y equals infinity. Our calculation matches the provided solution. Let's recap. We used L'Hopital's rule 3 times because we kept getting the indeterminate form infinity over infinity. Let's move on to the second part of question 1. Here we are given a formula for the numerical value of cos x defined as the limit of the inverse tangent of x squared, all over x, as x approaches 0. We need to calculate this value. As before, our first step is to attempt substitution. We'll substitute x equals 0. The inverse tangent of 0 is 0, so the numerator is 0 squared, which is 0. The denominator is also 0. This gives us another indeterminate form, 0 over 0. This means we can once again apply L'Hopital's rule. Remember, L'Hopital's rule applies to both infinity over infinity and 0 over 0. So we need to find the derivatives of the numerator and the denominator. The derivative of the numerator using the chain rule is 2 times the inverse tangent of x, multiplied by the derivative of inverse tangent of x. The derivative of the inverse tangent of x is 1 over 1 plus x squared. So the derivative of the numerator is 2 times inverse tangent of x all over 1 plus x squared. The derivative of the denominator, x, is simply 1. Now we substitute these derivatives back into our limit. We get the limit of our new numerator, 2 times inverse tangent of x, all over 1 plus x squared, divided by 1. Since dividing by 1 doesn't change anything, the expression simplifies to the limit of 2 times inverse tangent of x, all over 1 plus x squared. Now let's try substituting x equals 0 again. If we don't get an indeterminate form, we have our answer. The inverse tangent of 0 is 0, so the numerator is 2 times 0, which is 0. The denominator is 1 plus 0 squared, which is 1. 0 divided by 1 is 0. We've found a concrete value, so this is our answer. The numerical value of cos x is 0. This result confirms the solution in the memo. We successfully calculated a numerical limit by identifying an indeterminate form and applying L'Hopital's rule. We've completed question 1. Now let's move on to question 2, which focuses on derivatives and Taylor's theorem. The question gives us a function f of x equals 8 over the square root of x, and asks us to determine the simplest form of several expressions related to this function. It's always a good idea to rewrite a function involving radicals as a power function. This makes differentiation and algebraic manipulation much easier. The square root of x is x to the power of 1/2. Since it's in the denominator, we can write it as x to the power of negative 1/2. So f of x is 8 times x to the negative 1/2. Now let's tackle the first part. Part 2.11 asks for the first 3 terms of f of x plus h. To find these, we can use Taylor's theorem, which provides a formula for the expansion of a function f around a point x. The formula states that f of x plus h is approximately equal to f of x plus h times f prime of x plus h squared over 2 factorial times f double prime of x, and so on. We only need the first 3 terms, so we'll stop there. We need f of x, its first derivative f prime of x, and its second derivative f double prime of x. We already have the first term. The original function f of x is 8x to the negative 1/2. Next, let's find the first derivative using the power rule. We bring the exponent, negative 1/2, down and multiply it by the coefficient, 8. Then we subtract 1 from the exponent. Negative 1/2 minus 1 is negative 3/2. So f prime of x is 8 times negative 1/2 times x to the negative 3/2, which simplifies to negative 4x to the negative 3/2. For the third term, we need the second derivative, f double prime of x. We take the derivative of f prime of x. We bring down the exponent negative 3/2 and multiply it by negative 4. Negative 4 times negative 3/2 is positive 6. Then we subtract 1 from the exponent. Negative 3/2 minus 1 is negative 5/2. So f double prime of x is 6x to the negative 5/2. Now we substitute these derivatives into Taylor's expansion formula. F of x plus h is approximately f of x plus h times f prime of x plus h squared over 2 factorial, which is just 2, times f double prime of x. This gives us 8x to the negative 1/2 plus h times negative 4x to the negative 3/2 plus h squared over 2 times 6x to the negative 5/2. Finally, we simplify the coefficients. This gives us our answer. The first 3 terms of f of x plus h are 8x to the negative 1/2 minus 4hx to the negative 3/2 plus 3 squared x to the negative 5/2. The provided memo includes an unnecessary calculation using the binomial theorem, but this Taylor expansion approach is correct and more direct for these terms. We're continuing with question 2.1. In the previous scene, we found the first 3 terms of f of x plus h using Taylor's theorem. Now let's use that result to solve the next 2 parts of the question. Part 2.12 asks for the expression f of x plus h minus f of x. We simply subtract f of x, which is 8x to the negative 1/2, from our expansion of f of x plus h. The first term cancels out, leaving us with negative 4hx to the negative 3/2 plus 3a squared x to the negative 5/2. This matches the provided solution. Next, in part 2.1.3, we need to divide the previous result by h. We take the expression from part 2.12 and divide each term by h. In the first term, the h in the numerator and denominator cancel out. In the second term, h squared divided by h leaves us with h. So the simplified expression is negative 4x to the negative 3 halves, plus 3hx to the negative 5 halves. Finally, part 2.14 asks us to find the limit of this expression as h approaches 0. This entire expression is, by definition, the first derivative of f of x. In our simplified expression from part 2.1.3, we can now substitute h equals 0. The second term, 3hx to the negative 5 halves, becomes 0 because it's multiplied by h. This leaves us with just the first term, negative 4x to the negative 3 halves. This is our final answer, and it is exactly the first derivative, f prime of x, we calculated using the power rule at the beginning. This shows the consistency between the formal definition of the derivative and the rules of differentiation. The memo has a slight typo, incorrectly showing 4x to the negative 3 halves, but our result, 4x to the negative 3 halves, is correct. Let's continue with question 2.2. This section asks us to determine the derivative, dx, for two complex functions. Let's start with the first one, 2.21. The function y is a product of two terms, each raised to a power. This is a classic case for the product rule. The product rule states that if y equals f times g, then y prime equals f prime g plus fg prime. We need to identify our functions f and g. Let f of x be the first term, 5 plus log base 4 of x to the power of 4. Let g of x be the second term, 7x minus e to the power of sine 4x to the power of 5. Now we need to find the derivative of f and g separately, using the chain rule. To find f prime, we use the chain rule. The derivative of the outer function, something to the power of 4, is 4 times that something to the power of 3. We then multiply by the derivative of the inner function, which is the derivative of 5 plus log base 4 of x. The derivative of log base b of x is 1 over x ln b. So f prime is per times the first term cubed, all divided by x ln 4. Next, let's find g prime, which is a bit more involved, as it has an exponential function in the exponent. We'll use the chain rule here as well. The derivative of the outer function, something to the power of 5, is 5 times that something to the power of 4. We then multiply by the derivative of the inner function. Now we need to find the derivative of the inner function. The derivative of 7x is 7. For the second part, we need the derivative of e to the power of sine 4x, which is e to the power of sine 4x times the derivative of the exponent. The derivative of sine 4x is cosine 4x times the derivative of 4x, which is 4. So g prime is 5 times the second term to the power of 4 times the derivative we just calculated. Now we have all the pieces to apply the product rule. Dx is f prime times g plus f times g prime. We just need to plug in the expressions we found for fg, f prime, and g prime. The question specifies that simplification is not required. Comparing this expression to the memo, we see it matches exactly. This shows a very careful and correct application of the product and chain rules. Let's move on to the second function in question 2.2, which is even more complex. The function is y equals tan cubed of sine of a rational function. To differentiate this, we will need to use the chain rule multiple times. It's helpful to break this down into a composition of functions. The outermost function is something cubed. Inside that, we have the tangent function. Inside that, we have the sine function. And finally, inside the sine function, we have the rational function 7x squared plus 2 over x minus 3. We will apply the chain rule layer by layer, starting from the outside and working our way in. The derivative of something cubed is 3 times that something squared. So we get 3 times the entire expression in the brackets squared. Next, we differentiate the tangent function. The derivative of tan of u is sx squared of u. So we get sx squared of the inner function, sine of. And we must multiply by the derivative of that inner function, sin of. The derivative of sine of u is cos of u. So we get cosine of the inner function, our rational function, and we multiply by the derivative of that innermost function. Our final step is to find the derivative of the rational function. For this, we must use the quotient rule. The quotient rule states that if y equals f over g, then y prime equals f prime g minus f g prime, all over g squared. Let the numerator be f and the denominator be g. Applying the quotient rule, we get f prime g minus f g prime, all over g squared. Expanding the numerator, we get 14x squared minus 42x minus 7x squared minus 2. Combining the x squared terms, we get the simplified derivative, 7x squared minus 42x minus 2, all over x minus 3 squared. Now we can assemble the entire derivative by multiplying this result by the three terms we found from the chain rule. Putting it all together, dx is 3 times tan squared of the inner function, times secant squared of the inner function, times cosine of the rational function, times the derivative of the rational function. The provided memo combines the quotient rule part differently in the penultimate step, but the final expanded derivative for the rational function is consistent with our result. Our step-by-step application of the chain rule is correct and leads to the same final expression, albeit arranged slightly differently. Next, question 2.3 asks for the derivative of a function where the variable is in both the base and the exponent. The function is y equals the quantity 5 minus 4x raised to the power of 1 over x. When you have a variable in both the base and the exponent, a common and effective technique is called logarithmic differentiation. The strategy is to first take the natural log of both sides of the equation. This allows us to use the properties of logarithms to simplify the expression, specifically the power rule. Let's apply the natural logarithm to our function y. Now, we use the logarithm power rule, which says that the log of a power is the exponent times the log of the base. Applying this, the exponent 1 over x comes down as a multiplier. So we have natural log of y equals 1 over x times the natural log of 5 minus 4. Now that we've simplified the expression using logarithms, we can differentiate both sides with respect to x. We will differentiate the left side ln y and the right side, the product of 1 over x and ln 5 cosine. On the left side, we use the chain rule. The derivative of ln y is 1 over y times the derivative of y with respect to x, which is di dx. On the right side, we must use the product rule. Let f be 1 over x and g be ln 5 4x. The derivative of f is negative 1 over x squared. The derivative of g using the chain rule is 1 over 5 4x times the derivative of 5 4x, which is negative 4. Now we apply the product rule. F prime g plus f g prime. This gives us negative natural log of 5 minus 4x over x squared minus 4 over x times 5 minus 4x. Now we equate the derivatives of both sides. We have 1 over y times di dx equals our expression for the right side's derivative. Our goal is to solve for di quotak. We can do this by multiplying both sides by y. This gives us di dx equals y times the bracketed expression. Finally, we substitute back our original expression for y. Comparing this with the memo, we see a perfect match. Logarithmic differentiation allowed us to find the derivative of a very tricky function by simplifying the problem with logarithms first. It's a powerful tool for these types of functions. We've reached the last part of question 2, which deals with implicit functions. We are given an equation that defines a function implicitly. X cubed plus 5xe minus 2y squared equals 8. First, we need to find the derivative. For this, we use implicit differentiation, which means we differentiate every term in the equation with respect to x. The key idea here is to remember that y is a function of x. So when we differentiate a term involving y, we must use the chain rule. Differentiating x cubed gives us 3x squared. For the term 5xe, we need to use the product rule, treating 5x as our first function and y as our second. The derivative of 5x is 5. The derivative of y with respect to x is dx, so the derivative is f prime g plus f g prime, which is 5 times y plus 5x times di slag. For the term negative 2y squared, we use the chain rule. The derivative of something squared is 2 times that something. So we have negative 2 times 2y, which is negative 4y. Then we multiply by the derivative of the inner function, y, which is di slash dx. This gives us negative 4y d. And finally, the derivative of the constant 8 is 0. Now we can put all these pieces together and solve for di d. The differentiated equation is 3x squared plus 5y plus 5x dx minus 4 psi dx equals 0. We need to isolate the dx term. First, group all terms containing dx on one side and all other terms on the other. We can factor out dx. Then, to get dx by itself, we divide both sides by the quantity 5x 4y. So the derivative dx is negative 3x squared minus 5y all over 5x minus 4y. This matches the solution in the memo. Let's continue with the second part of question 2.4. We are asked to determine the equation of the tangent line to the graph of the implicit function at the point 1, 2. The equation of a line can be written in the form y equals mx plus c, where m is the gradient and c is the y-intercept. A tangent line is just a straight line, so we need to find its gradient and then its equation. The gradient of the tangent line to a curve at a specific point is given by the derivative evaluated at that point. In the previous part, 2.4.1, we found the formula for the derivative, dx. The derivative is negative 3x squared minus 5y, all over 5x minus 4y. To find the gradient at the point 1, 2, we substitute x equals 1 and y equals 2 into this formula. The numerator is negative 3 minus 10, which is negative 13. The denominator is 5 minus 8, which is negative 3. A negative divided by a negative is a positive, so the gradient of the tangent line is 13 over 3. Now we have the gradient and a point on the line. We can use the point gradient form to find the equation. The point gradient formula is y minus y1 equals m times the quantity x minus x1, where x1, y1 is the point 1, 2, and m is 13 over 3. Substituting these values, we get y minus 2 equals 13 over 3 times the quantity x minus 1. Now we can rearrange this into the slope-intercept form, y equals mx plus c, to find the y-intercept c. First, distribute the 13 over 3 into the brackets, which gives us y minus 2 equals 13x over 3 minus 13 over 3. Then we add 2 to both sides of the equation. To add them, we find a common denominator for 2, which is 3. So 2 becomes 6 over 3. Adding the fractions, we get negative 13 over 3 plus 6 over 3, which is negative 7 over 3. So the final equation of the tangent line is y equals 13 over 3x minus 7 over 3. This matches the equation provided in the memo. We successfully used our calculated derivative to find the gradient of the tangent line and then determined its equation. We have completed question 2. Now let's begin question 3.1. which involves analyzing the turning points of a cubic function. In this problem, we are given the function f of x equals x cubed minus 2x squared plus 4. Part 3.11 asks us to find the coordinates of the turning points of this function. Turning points are also known as stationary points, local maxima, or local minima. A key property of turning points is that the gradient of the curve is 0. The gradient is represented by the first derivative of the function. Therefore, to find the x-coordinates of the turning points, we must set the first derivative equal to 0. First, let's find the first derivative of our function. The derivative of x cubed is 3x squared. The derivative of negative 2x squared is negative 4x, and the derivative of the constant 4 is 0. So f prime of x is 3x squared minus 4x. Now we set this derivative to 0 to find the x values. The equation is 3x squared minus 4x equals 0. We can solve this by factoring out a common factor of x. This gives us x times the quantity 3x minus 4 equals 0. For this product to be 0, one of the factors must be 0. So we have two possible x-coordinates for our turning points. X equals 0, or x equals 4 over 3. We've found the x-coordinates. Now we need to find the corresponding y-coordinates by substituting these x values back into the original function, f of x. For x equals 0, f of 0 is 0 cubed minus 2 times 0 squared plus 4, which equals 4. This gives us our first turning point, our 4. For x equals 4 over 3, we substitute that value into f of x. We get 4 over 3 cubed minus 2 times 4 over 3 squared plus 4. This calculates to 64 over 1 minus 32 over 9 plus 4. To add these fractions, we find a common denominator, which is 27. So we get 64 minus 96 plus 108, all over 27. The result is 76/27. As a decimal, this is approximately 2.815. This gives us our second turning point, 4/3 and 76/27. So we have found the coordinates of both turning points by setting the first derivative to 0 and solving for x, then substituting those values back into the original function. We found the turning points for f of x. Now let's complete the next two parts of the question, which are related to graphing the function. We need to sketch the graph of f of x, and to do that, we'll start by making a table of values. Part 3.12 asks for a table of values for f of x for integers x ranging from -2 to +3. We'll substitute each integer value of x into the function f of x equals x cubed minus 2x squared plus 4. For x equals -2, we get -8 minus 8 plus 4, which is -12. For x equals -1, we get -1 minus 2 plus 4, which is 1. We've already calculated f of 0 to be 4 as it's a turning point. For x equals 1, we get 1 minus 2 plus 4, which is 3. For x equals 2, we get 8 minus 8 plus 4, which is 4. For x equals 3, we get 27 minus 18 plus 4, which is 13. Here is our complete table of values. This will give us a good set of points to plot the graph. Now let's use this table and our turning points to draw the graph for part 3.12. First, we plot all the points from our table and the two turning points we calculated. We plot our integer points, 2/12, 1, 1, 0, 4, 1, 3, 2, 4, and 3, 13. We also plot our turning points, 0, 4, and 4, 3, 6, 27, which is approximately 1.33, 2.815. Now, we draw a smooth curve connecting these points. The curve should pass through the turning points. Notice that the graph is generally a cubic function shape. It rises to a local maximum at 0, 4, then falls to a local minimum at approximately 1.33, 2.858, and then rises again. This shape is characteristic of a cubic function with a positive leading coefficient. This neat graph, showing the correct shape and the turning points, completes this section of the question. The Memo's graph is correct, but let's carefully check the labels. The point, 2, 4, is plotted, which is incorrect based on our table. The local minimum is correctly shown. Always double-check your points. We've analyzed and graphed our cubic function. Now for the final part of question 3.1. Part 3.14 gives us an estimated value of a root, x0 equals -1.2. We are asked to use Taylor's or Newton's method twice to find a better approximation of this root to 3 decimal places. Newton's method, also known as the Newton-Raphson method, is an iterative process for finding the roots of a real-valued function. The formula for Newton's method is the next approximation, xn plus 1, is equal to the current approximation, xn, minus the function value at that point, fxn, divided by the derivative at that point, fx. We need to perform this calculation twice. This means we'll find x1 and then x2. We are given our starting point, x0, which is -1.2. To use the formula, we need two things, the function fx and its derivative fx. Our function is f of x equals x cubed minus 2x squared plus 4. Its derivative, which we already found in part 3.1.1, is f prime of x equals 3x squared minus 4. Let's calculate our first approximation, x1. x1 equals x0 minus f of x0 over f prime of x0. We need to evaluate the function and its derivative at our starting point. x0 equals -1.2. f of -1.2 is -0.60. f prime of -1.2 is 9.12. Now we plug these values into the formula. x1 is -1.2 minus -0.608 over 9.12. This simplifies to -1.2 plus 0.0666666, which gives us our first approximation, x1 approximately -1.133. This is a better approximation, but we need to do it twice. So we'll use x1 as our new starting point for the next iteration. Our new starting point, x0, is now -1.3. We need to find f and f prime at this new point. Using a calculator, f of -1.33 is approximately -0.021, and f prime of -1.33 is approximately 8.383. Now we apply the Newton's method formula again. x2 equals our new x naught, negative 1.33, minus negative 0.021 over 8.383. This simplifies to negative 1.133 plus approximately 0.0025, which gives us our second approximation. x2, approximately negative 1.130. This is the value corrected to 3 decimal figures as requested. The memo's calculation is also correct, but it's important to be careful with negative signs. We've finished with our function analysis. Now let's move on to the first word problem of the paper. Question 3.2 describes a rectangular shell made of steel bars. The ends are square, and the total length of the steel bars used is 144 meters. We need to find the dimensions of the box that will give the maximum possible volume. This is a classic optimization problem. We want to maximize a function, volume, subject to a constraint, the total length of the steel bars. Let's first visualize the box and define our variables, as suggested by the problem description. The problem states the ends are square. The diagram shows the sides of this square end are of length x. The length of the box is y. Let's define our variables. Let x be the side length of the square end, and let y be the length of the box. Now let's use our constraint. The total length of the steel bars is 144 meters. To find this total length, we need to count all the edges of the box. Let's look at our diagram. The box has 4 vertical edges, each of length x. The top and bottom square ends each have 4 edges of length x. In total, there are 8 edges of length x. There are also 4 horizontal edges along the length of the box, each of length y. So the total perimeter, P, is 8x plus 4y. We are told this is 144. Now we can write our constraint equation. The constraint equation is 8x plus 4y equals 144. Our goal is to maximize volume. Let's find an expression for the volume V of the box. The volume of a rectangular prism is the area of the base times the height. Our base is a square of side x, so its area is x squared. The length, or height, is y. So the volume V equals x squared y. We now have an equation for volume with 2 variables, x and y. To maximize it using calculus, we need an equation with only one variable. This is where our constraint comes in. We can use the constraint equation to express y in terms of x. Subtracting 8x from both sides gives 4y equals 144 minus 8x. Dividing by 4 gives y equals 36 minus 2x. This matches the memo. Now we substitute this expression for y into our volume equation. The volume 5 is x squared times the quantity 36 minus 2x. Distributing the x squared, we get v of x equals 36x squared minus 2x cubed. This is the function we need to maximize. To find the maximum volume, we find the critical points by taking the derivative of v with respect to x and setting it to 0. The derivative, v prime of x, is 72x minus 6x squared. Setting this to 0, we have 72x minus 6x squared equals 0. We can factor out a common factor of 6x. This gives us 6x times the quantity 12 minus x equals 0. This gives us 2 possible solutions for x. Either 6x is 0, which means x is 0, or 12 minus x is 0, which means x is 12. An x value of 0 would result in a box with no square end, and therefore no volume. So x equals 0 is not a viable dimension for a real box. We can also confirm that x equals 12 is a maximum using the second derivative test. But for this problem, the context tells us which value to use. Therefore, x equals 12 is our solution for the side of the square. Now we need to find the corresponding length y using our constraint equation. Substituting x equals 12 into y equals 36 minus 2x, we get y equals 36 minus 24, which is 12. So y is also 12 meters. The dimensions that yield the maximum volume are x equals 12 meters and y equals 12 meters. This means the box is actually a perfect cube. This result matches the memo perfectly. Our next question, 3.3, is a related rates problem. This type of problem involves finding the rate of change of one quantity in terms of the rate of change of another related quantity. The problem states that the surface area of a snowball is decreasing at a rate of 6 square meters per hour. We need to find out how fast its diameter is changing at the exact moment its radius is 2 meters. The problem gives us a helpful hint. The formula for the surface area A of a sphere is 4 pi r squared. First, let's identify what information is given and what we need to find. We are told the surface area is decreasing at 6 square meters per hour. Decreasing tells us the rate is negative, so d dt equals -6. We are asked to find how fast the diameter is changing, which is the rate d dd. This rate should be found when the radius, r, is 2 meters. Our strategy will be to relate a and d. We are given a in terms of r. We can relate d and r and then put it all together. The fundamental relationship between diameter d and radius r is that the diameter is twice the radius. This means r is d divided by 2. Now we can express the surface area A directly in terms of d. This is a crucial step that simplifies the differentiation. We start with the formula A equals 4 pi r squared. We substitute d over 2 for r. Squaring d over 2 gives d squared over 4. The 4 in the numerator and denominator cancel out, leaving us with a simple and elegant formula. A equals pi d squared. This matches the memo. Now we can differentiate this equation with respect to time, t. The derivative of a with respect to t is dA/dt. On the right side, we use the chain rule to differentiate pi d squared with respect to t. The derivative of pi d squared with respect to d is 2 pi d. By the chain rule, we must multiply this by the derivative of d with respect to t, which is dE t. We now have an equation that relates all our quantities. Let's substitute the known values. We know dA/dt is -6. We know r is 2 meters, which means the diameter d is 2 times 2, or 4 meters. The only unknown left is ddd, which is what we need to find. Substituting these values, our equation becomes -6 equals 2 pi times 4 times dd/dt. This simplifies to -6 equals 8 pi times dd/dt. To solve for dd/dt, we simply divide both sides by 8 pi. dd/dt equals -6 divided by 8 pi. Simplifying the fraction -6 over 8, we get -3 over 4. The rate of change of the diameter is -3 over 4 pi meters per hour. The question also asks for a decimal value. Calculating this on a calculator, we get approximately -0.2387. Rounding to 3 decimal places, the rate is approximately -0.239 meters per hour. The memo correctly provides both the exact fractional answer and the rounded decimal answer. So when the radius is 2 meters, the diameter of the snowball is decreasing at a rate of 0.239 meters per hour. We've finished with differentiation and its applications. Now we're moving on to our first integration problem. In question 4.1.1, we need to evaluate the integral of the quantity 2x minus 1, divided by the quantity 2x squared minus 2x plus 5 squared. Looking at this integral, we see a function in the denominator that is squared and a multiple of its derivative in the numerator. This is a clear indicator that integration by substitution, specifically u substitution, will be the most effective method. The strategy for u substitution is to identify a part of the integrand, which we'll call u, whose derivative do is also present, or a constant multiple of it. Let's try setting u equal to the expression inside the parentheses in the denominator. Now we find the differential do by taking the derivative of u with respect to x and multiplying by dx. The derivative of u is 4x minus 2. So do equals the quantity 4x minus 2 times dx. Now let's look back at our integral. The denominator contains u squared. The numerator is 2x minus 1 dx. How does this relate to du? Notice that the expression in the numerator, 2x minus 1, is exactly 1/2 of our differential do. If we divide do by 2, we get 1/2 of do equals 2x minus 1 dx. We now have everything we need to rewrite the integral entirely in terms of u. We substitute u into the denominator, making it u squared. We substitute 1/2 do for the entire numerator, 2x minus 1 dx. We can pull the constant 1/2 out in front of the integral sign. And to prepare for integration, we can rewrite 1 over u squared as u to the power of -2. This new integral is a simple power rule integral, which is easy to solve. Using the power rule, we add 1 to the exponent and divide by the new exponent. So the integral of u to the negative 2 is u to the power of negative 1 divided by negative 1. Don't forget the constant of integration, c. Don't forget the p. This simplifies to negative 1 over 2u plus c. We are not done yet. The final answer must be in terms of x, not u. We must substitute our original expression for u back into the answer. Recall that u equals 2x squared minus 2x plus 5. Substituting this back gives our final answer. The integral is negative 1 over 2 times the quantity 2x squared minus 2x plus 5 plus c. This result matches the memo exactly, confirming our u substitution method was correct. Next is question 4.1.2, a trigonometric integral. These can often be solved in a couple of different ways. Let's explore the first method shown in the memo. The strategy for integrals of the form sine to a power and cosine to a power is to use the Pythagorean identity. The general rule is, if the power on sine is odd, save one sine term and convert the rest to cosine using sine squared equals 1 minus cosine squared. If the power on cosine is odd, save one cosine term and convert the rest to sine using cosine squared equals 1 minus sine squared. In our integral, both powers are odd. In the memo's first method, it focuses on the sine term. The power on sine is 5, which is odd. So, we'll split sine to the 5th into sine to the 4th times sine. This sine term at the end will be part of our do when we do u substitution later. Next, we rewrite sine to the 4th as sine squared squared. Then we use the Pythagorean identity. Sine squared equals 1 minus cosine squared. This converts our expression to only involve cosine and that single sine x dx term. Now that everything is in terms of cosine, we are ready for u substitution. It makes sense to let u be cosine x. Let's set u equals cosine x. Then do equals the derivative of cosine x, which is negative sine x times dx. The sin x dx part in our integral is almost do. It's the negative of do. So sin x dx equals negative do. Now we substitute into our integral. The integral becomes the integral of 1 minus u squared squared times u cubed times negative do. Let's expand the squared term. 1 minus u squared. Squared is 1 minus 2u squared plus u to the 4th. Then we distribute the u cubed. Now we have a simple polynomial to integrate. We apply the power rule to each term. The integral is negative of 1/4 u to the 4th minus 1/3 u to the 6th plus 1/8 u to the 8th plus c. Simplifying the coefficient of the middle term and distributing the negative sign, we get negative 1/4 u to the 4th plus 1/3 u to the 6th minus 1/8 u to the 8th plus c. The final step, as always, is to substitute back for u. Substituting u equals cosine x, we get our final answer. Negative 1/4 cosine to the 4th of x plus 1/3 cosine to the 6th of x minus 1/8 cosine to the 8th of x plus c. This perfectly matches the memo's first solution path. Let's revisit question 4.1.2 and explore the second method provided in the memo. This will show us that there can be multiple valid paths to the same solution. Our integral is the integral of sine to the 5th of x times cosine cubed of x dx. In our first method, we focused on the odd power of sine. For this second method, the memo focuses on the odd power of cosine. The power on cosine is 3, which is odd. Save one cosine term and convert rest to sine. Following the strategy, we save one cosine term. We split cosine cubed into cosine squared times cosine. This cosine x dx at the end will be part of our do. Now we use the Pythagorean identity to convert the cosine squared term to sine. Cosine squared of x equals 1 minus sine squared of x. The integrand is now in terms of sine, with a lone cosine x dx term. This is perfect for u substitution. This time, we'll let u be sine x. Let u equal sine x. Then do is the derivative of sine x, which is cosine x times dx. We can now substitute into the integral. The integral becomes the integral of u to the 5th times 1 minus u squared times do. We distribute the u to the 5th term into the parentheses. This is again a simple polynomial integral. Using the power rule, the integral is 1/6 u to the 6th minus 1/8 u to the 8th plus c. Finally, we substitute back for u. Substituting u equals sine x, we get our final answer, 1/6 sine to the 6th of x, minus 1/8 sine to the 8th of x plus c. This perfectly matches the memo's second solution path. Now you might be asking, which answer is correct? They look different. The remarkable thing about indefinite integrals is that the answer can be expressed in different but algebraically equivalent forms. Using a trigonometric identity like sin squared plus xi squared equals 1, you can show that both of our answers are the same. Let's do a quick check. If you substitute sin squared equals 1 minus cos squared into our second answer, you can rearrange it to get the first answer, up to the constant of integration. So, both solutions are correct. Question 4.1.3 presents an integral of a rational function. When we have the integral of a rational function where the degree of the numerator is greater than or equal to the degree of the denominator, our first step should always be to perform polynomial long division. In this case, the numerator is degree 4 and the denominator is degree 1, so we must divide. We set up our long division with the numerator as the dividend and the denominator as the divisor. We start by asking, what do we multiply 2x by to get 2x to the 4th? The answer is x cubed. We write x cubed above. We multiply x cubed by the entire divisor, 2x plus 3, to get 2x to the 4th plus 3x cubed. Then we subtract this from the dividend. 2x to the 4th minus 2x to the 4th is 0. X cubed minus 3x cubed is negative 2x cubed. We bring down the next term, x squared. Now we ask, what do we multiply 2x by to get negative 2x cubed? The answer is negative x squared. We write this next in our quotient. Multiply negative x squared by the divisor to get negative 2x cubed minus 3x squared. Subtracting this gives 0 plus 4x squared. Bringing down the next term, we get 4x squared plus 0x. What do we multiply 2x by to get 4x squared? The answer is 2x. Multiply 2x by the divisor to get 4x squared plus 6. Subtracting gives negative 6. Finally, we bring down the minus 2. What do we multiply 2x by to get negative 6x? The answer is negative 3. Multiplying negative 3 by the divisor gives negative 6x minus 9. Subtracting this from negative 6x minus 2 gives us a remainder of 7. We can now rewrite our original integral. It is equal to the integral of the quotient plus the remainder over the divisor. So the integral is the integral of x cubed minus x squared plus 2x minus 3 plus 7 over 2x plus 3, all with respect to x. This matches the memo's result. Now we integrate each term separately using the power rule for the first 4 terms and the chain rule for the last term. The integral of x cubed is x to the 4th over 4. The integral of negative x squared is negative x cubed over 3. The integral of 2x is x squared. The integral of negative 3 is negative 3x. For the last term, 7 over 2x plus 3, we use a form of u substitution. Let u be 2x plus 3, so do is 2 dx. This means dx is 1/2 deu. The integral becomes the integral of 7 over u times 1/2 do, which is 7 over 2 times the natural log of the absolute value of u. Substituting back, we get 7 over 2 times the natural log of the absolute value of 2x plus 3. Putting it all together, our final answer is x to the 4th over 4 minus x cubed over 3 plus x squared minus 3x plus 7 over 2 times the natural log of the absolute value of 2x plus 3 plus c. This matches the memo's answer exactly, confirming that polynomial long division was the correct first step, followed by integrating each resulting term. Question 4.14 asks for the integral of a product of 2 functions. The integrand is x times log base 3 of 4. This is a product and u substitution doesn't work here. This tells us we need to use integration by parts. Integration by parts is a technique for integrating the product of 2 functions. It's often written in a formulaic way. The integral of u dv equals u times v minus the integral of v du. The most important part of this method is choosing which part of the integrand is u and which part is dv. A helpful mnemonic for this is liete. Liete stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. It's a general guide for choosing u. We want to choose u to be the function that comes first in this list. In our integral, we have a logarithmic function, log base 3 of 4x, and an algebraic function, x. Logarithmic functions appear before algebraic functions in Liade. So we'll let u be the logarithmic part, let u equal log base 3 of 4. Then the remaining part, x dx, must be our dv. Now we need to find do by differentiating u and find v by integrating dv. To find do, we differentiate log base 3 of 4. The derivative of log base b of fx is f prime of x over fx, ln b. So do is 4 over 4x ln 3 dx, which simplifies to 1 over x ln 3 dx. To find v, we integrate x dx using the power rule. The integral of x is x squared over 2. We now have all 4 parts of our formula. Let's substitute them in. The integral equals u times v minus the integral of v du. Let's simplify the new integral. We can pull the constants, and 1/3 outside the integral. The term x squared over x simplifies to x. We integrate x, which is x squared over 2. Then we multiply by the constant outside. The coefficient becomes 1 over 4 ln 3. The provided memo combines the second term differently. The memo writes it as x log base 2 of x minus 1 over 2 ln 3 times x squared plus c. There is a typo in the log base. It should be base 3. If we correct that, their answer is x log base 3 of x minus x squared over 2 ln 3 plus c. This is a partial match. Let's carefully compare. Our answer is x squared over 2 log base 3 of 4x. The memo has x log base 3 of x. This suggests the memo may have chosen u and dv differently, or made a simplification using logarithm properties. However, using Liade is the standard, most reliable way to choose u, and our differentiation and integration steps are correct. Therefore, our answer of x squared over 2 log base 3 of 4x minus x squared over 4 ln 3 plus c is the correct result of integrating by parts using the Liade rule. Our final question for today, question 4.2, asks us to integrate another rational function, but this time using a different method. We need to integrate the quantity 2x plus 7 divided by x squared plus x minus 2. The problem specifically asks us to do this by first resolving the integral into partial fractions. This method is used to decompose a complex fraction into a sum of simpler fractions, which are easier to integrate. It is applicable when the degree of the numerator is less than the degree of the denominator, which is true in our case. The first step is to factor the denominator. X squared plus x minus 2 factors into x plus 2 times x minus 1. Since these are distinct linear factors, we can write the original fraction as a sum of 2 simpler fractions. We hypothesize that our fraction is equal to some constant a over x plus 2 plus some constant b over x minus 1. Our goal is to find a and b. To solve for a and b, we first clear the denominators. We multiply the entire equation by the common denominator, x plus 2 x minus 1. This leaves us with the equation 2x plus 7 equals a times x minus 1 plus b times x plus 2. The simplest way to find a and b is the substitution method, also known as the Heaviside cover-up method. We choose values of x that make one of the terms on the right side 0. Let's start by letting x equal 1. This will make the term ax1 equal to 0. Substituting x equals 1 into our equation gives us 2 times 1 plus 7 equals b times the quantity 1 plus 2. This simplifies to 9 equals 3b. Dividing by 3, we find that b equals 3. Next, let's let x equal negative 2 to make the term bex plus 2 equal to 0. Substituting x equals negative 2 gives us 2 times negative 2 plus 7 equals a times the quantity negative 2 minus 1. This simplifies to 3 equals negative 3a. Dividing by negative 3, we find that a equals negative 1. We have found our constants. A is negative 1 and b is 3. This matches the memo. Now we can rewrite our original integral in its simpler partial fractions form. The integral of 2x plus 7 over our denominator is equal to the integral of -1 over x plus 2 plus 3 over x minus 1. We can integrate each term separately. The integral of 1 over u is the natural log of u. So the first integral is negative the natural log of the absolute value of x plus 2. The second integral is 3 times the natural log of the absolute value of x minus 1. Using a property of logarithms, we can move the coefficient 3 into the argument as an exponent. This gives us the natural log of the absolute value of x minus 1 cubed. So the final answer is negative the natural log of x2 plus the natural log of x1 cubed plus c. Let's compare this to the memo. The memo's answer is negative ln x2 plus 3 ln x1 plus c, which is exactly the same as our penultimate step. We can also combine these into a single log term. Using the log property that ln a minus ln b is ln of a over b, we get our final answer. The natural log of the absolute value of x minus 1 cubed divided by x plus 2 plus c. This shows that the memo's answer is correct and our further simplification is also valid. We've made it through questions 1, 2, and 3, and a good portion of question 4. To keep our tutorials focused, we'll stop here for this video. We've covered a wide range of important calculus topics, from limits and derivatives to their applications in optimization and related rates. We also explored various integration techniques, including substitution, integration by parts, and partial fractions decomposition. Thank you for watching. If you found this tutorial helpful, please consider subscribing to Math Zone African Motives for more step-by-step math tutorials. We'll continue this paper in our next video, covering questions 5 and 6.